Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will continue our learning on Prosper software, very good well modeling software. And today's topic is about intermittent gas lift. So it will be very interesting and hopefully useful for all of us. Okay, so as usual, we start by opening this tab. Okay, you can follow me, fluid description, fluid oil and water, method black oil, and separator single stage separator, no emulsion, disable PVT warning, water viscosity, use default correlation, viscosity model Newtonian fluid, and for the well, flow type tubing flow, well type producer, and for the method, now you open the drop down menu and we will find this one gas lift continuous, this one gas lift intermittent. Okay, and the type gas lift. You can also type in the user information, user comments, and for the calculation type, this one offshore model rough approximation. Okay, it's sufficient. Range, full system, brine properties, default, type case hole, send control none, reservoir inflow type single branch, and no gas conning. Okay, click done. Okay, now we go to the second section. It's a PVT input data. This one. Okay, I have my data. You can use your own data or you can follow me. Solution GOR 800, SCF per STB, oil gravity 37, gas gravity 0.76, water salinity 23,000 ppm, no H2S, no CO2, and no nitrogen. For the bubble point, RS, and oil formation volume factor, we will use Galasso correlation. Oil viscosity correlation, we will use Bill et al. Correlation. Other data, viscosity model, Newtonian fluid. Hopefully, we can cover non-Newtonian fluid. Emulsion, no emulsion. Okay. If you have laboratory data to be matched, you can also use this data match, PVT matching, the pressure, GOR, BO, oil formation volume factor, and oil viscosity, and the temperature, and also the bubble point. And then you can press match button and obtain the matching. That is better. Okay. But in this case, we don't have that data and we can start by using this PVT data. Okay. So click cancel, click done. All right. So from here, we will go to IPR model section. Okay. PI entry. I will use this one, PI entry. Okay. And then for the reservoir pressure, it is 2000. Reservoir temperature 210. Water cut 80%. Total GOR 800. Automatically imputed by Prosper using the previous PVT data. No compaction permeability model and no relative permeability. And then we can use for the PI productivity index, let's say 5. Okay, 5. Calculate. I get the AOF maximum flow rate 6,900. But I think I will choose Darcy instead. Okay, Darcy. All right, so for Darcy and the mechanical geometric skin, I will enter skin by hand. Okay, so for the model data, reservoir model, the permeability 50, the thickness of the reservoir 100, with drainage area of 500 acres, DHC factor 31.6, assuming radial reservoir, and wellbore radius 0.354. With mechanical geometric skin 1, okay, and I don't enable Wong Clifford model. Okay, so far so good. Calculate. All right, so this is the AOF maximum flow rate, 8,300. Plot results. I will plot rate for the x-axis and pressure for the y-axis. I don't need to plot the temperature. Click done. Okay, so this is my IPR starting from the reservoir pressure of 2000 down to atmospheric pressure. This is the theoretical AOF, theoretical maximum flow rate. Okay, so far so good. And from here, we can click finish, done, done. All right, so this is our IPR. And you can see we have a new tab here. This is actually the tab for intermittent gas lift input data. But we can input the data here after using design section. Okay, later on, we will go to design section here. Okay, I skip this section first, and then I go to equipment data section. We will edit deviation survey, downhole equipment, geothermal gradient, and also maybe you want to check average heat capacities. Okay, click edit. Okay, so you can follow me. Measured depth through vertical depth. Okay, all right. 1005, 1000. Okay, and then 4075 at 4000, 7700, 7500. Lastly, the depth of the reservoir 9000 for TVD. Okay, plot. We have deviated well. Finish. Click done. All right. So the next one is the downhole equipment. Christmas tree at 600 feet. And then tubing. Open the drop-down menu. Down to 1000. 4.052. Tubing inside roughness as per default. Tubing outside diameter 4.8, quite big. Tubing inside or tubing outside roughness. Okay, so we have roughness for inside of the tubing and also outside of the tubing and also inside of the casing. All right, and in this case, I will use default roughness and casing inside diameter 6.4, rate multiplier 1, and I will have subsurface safety valve with smaller diameter 3.72. Tubing again down to depth of 9000 with the same size. All right, for the inside diameter, outside diameter, and also the casing ID 6.4. And lastly, I will have casing here down to the bottom of the well 9275 with casing inside diameter the same 6.4. Default casing inside roughness and rate multiplier all 1. Okay, click done. Now for the geothermal gradient. This is important for heat transfer calculation. Overall heat transfer coefficient 8.6. Okay, at 0 depth, the temperature is 60 degrees Fahrenheit. At the level of the wellhead 600. It is a bit cooler, 40 degrees Fahrenheit. And for the depth of the reservoir 210. You can check the plot. Okay, so we have linear trend here. Okay, finish, done. And you can check the average heat capacities used in Prosper for oil, gas, and water. Okay, click done, and you can check the summary. This is the equipment summary and drawdown hole, Christmas tree, tubing, showing the inside diameter, outside diameter, and also the casing inside diameter, 6.4 inches. And we have here the SSSV, subsurface safety valve, tubing after the safety valve, and casing all the way through from the top to the bottom. Okay, done. So far, so good. All right, let's wait for the well picture. Okay, so this is our well. Okay, so from here, we can go to this one, design, and you will find intermittent gas lift. Okay, so it's going to be quite easy. Surface injection pressure, 1,500, the available injection pressure, and we will set the injection depth at depth of 7,430 with the gas gravity for the gas lift gas 0.68 and the operating wellhead pressure 250 psig and valve port size 24 per 64 inches. Okay, so you can try several port sizes. Okay, but in this case, let's say I already do the evaluation and then I have this one, this size, 24 by 64. Water cut as per IPR data, 80% with tubing liquid level. I want to set it at 4,500 feet. And of course, there will also be liquid level. Okay, so let's press the calculate very, very fast. Okay, and let's open it. So we will have downhole injection pressure at the depth of this injection depth. Okay, and we will also have downhole pressure. Okay, downhole pressure. This is the downhole injection pressure. This is the downhole pressure, the tubing pressure or the tubing production pressure, bottom hole flowing pressure to be exact. And it's interesting, we can also get the slug velocity, bubble velocity for our flow regime, and the gas injection rate at this condition is this one, 52,000 SCF per day. Fallback, there will be fallback in this one. Produce slug length. Okay, so now we will produce slugs and the length is quite long. Okay, and you need to inform the surface facility engineers regarding this slug. This slug can bring trouble, I think. Okay, due to the impact it brings to the surface equipment. And produce slug volume almost 17 barrels. And this is the pressure, the ratio of casing pressure and the slug pressure produced by accumulated slug length or produced or accumulated slug length, starting slug length by valve depth, the time to surface. Okay, this one, cycle frequency. Okay, so this is important, the cycle frequency for our intermittent gas lift operation. Okay, so it means that now we inject the gas. Okay, inject the gas, enable the flow, and then we will stop the injection. Okay, for almost 4 hours. Okay, oh, I think let's be careful here. Per hour, we will have almost 4 cycles. Okay, so within 1 hour, we will have 4 injections and 4 shut-ins. Okay, 4 injections and 4 without injection. Okay, so that's the cycle. And at this operation state, we will produce at rate of 1,537 stock tank barrel per day. So that's quite satisfying. Okay, and let's check the valves. And we will select constant surface closing pressure. Okay, and you can follow me. For this one, we have for the input data, surface injection pressure, unloading fluid gradient. Okay, after completion, for example, all right, surface injection pressure, again, 1,500 psig, unloading fluid gradient, for example, after the completion, right, because we still need to make our system prepared for unloading operation. 0.46, for example, heavier than water because of I use completion fluid, which involve brine, so it is quite heavier than the usual water, okay, or fresh water. And for the spacing factor, I will allow 0.1 psi per foot, okay. Wellhead pressure, same 250, and surface closure pressure or surface closing pressure 800. So it means that at surface condition at 800 psig, the valve, the injection valve, the gas lift valve will close. Okay. And of course, you need to translate the pressure to the bottom hole pressure at each depth. Okay. At the depth at which the valve is installed. And then maximum depth of injection 7,500 feet. Okay, so far so good. Now we can easily calculate the results using this one. Press calculate. Okay, so again, that's very quick. We have this one, the wellhead depth. Okay, this one, the spacing pressure or wellhead pressure, closing pressure, starting from injection pressure of 1,500. Okay, and we have 4 valves at these depths with spacing pressure, okay, closing pressure, and injection pressure. Okay, so this is the results. And let's check the plot. The green one, spacing pressure. Okay. And this one, closing pressure, the red line. Okay, and then the blue line is the injection pressure. Okay, the injection pressure. Okay, so far so good. So very easy to design the intermittent gas lift using Prosper. Very interesting. And this one, the gradient, is of course the line created using gradient of this one, unloading fluid gradient of 0.46 psi per foot. Okay, so let's check this plot. Okay, closing pressure is the pressure below which injection valve will close, the gas lift valve will close. Okay, whereas the spacing pressure, we can also say this is the producing pressure. Okay, the tubing pressure during production. Okay, or during unloading. Okay, so far so good. So we can click done, click done. All right, and then for this one, we can go. You can see the results are distributed or populated into this section automatically. You can see the surface injection pressure of 1,500, the injection depth at this one. Okay, you can see the symbol or the picture of the operating valve for intermittent injection, right? It's not continuous injection, it's intermittent injection, but the injection will be located at this depth. And this is the gas gravity for the gas lift gas, 0.68. Wellhead pressure during production, 250. And this is the valve port size, water cut 80%, and tubing liquid level 4,500. Okay, so far so good. And as usual, the last section is of course the calculation. Go to system, IPR VLP, and then for the top node pressure, the wellhead pressure, let's say now is 250. Okay, water cut 80%, total GOR 800. Calculate. Okay, let's wait for the calculation. Wow, something happened here. Okay, IPR versus VLP. Okay, interesting. Let's increase the wellhead pressure, 500. Calculate. Okay, so this red line is of course the IPR, you can see here, whereas for the blue line is the VLP. Okay, and what about if we have water cut of 0? I'm just going to try. All right, still there's a problem. Very dynamic here. Okay, all right. Okay, now I will create some cases. Okay, so I will have cases for reservoir pressure. Okay, and then for the top node pressure, and lastly water cut. Okay, for the reservoir pressure, I only will have one scenario, 4,000. For the top node pressure, I have 250, 500, and 750. Whereas for the water cut, I will start from 0, 10, 20, 30, 40, 50, 60, 70, 80, lastly 90. Click done. Okay, so I have several sensitivity cases, and then I will just press calculate. Okay, let's wait. All right, so we have completed the calculations for all the cases, but you can see we have this IPR, but still the VLP is like this. I think it's because this VLP is created as usual, but in reality, the intermittent production doesn't allow us to have the shape of the VLP like usual, like for the continuous operation. So I think instead of using or relying or obtaining the operating point to get the production rate, I think in this case we can rely the results from here. So what we will get is actually the daily production obtained from this design. Okay. So the daily production rate is 1,537 stock tank barrel per day. So that will be my take. The production rate using intermittent gas lift is this one. Okay, so we get the result, but I think let's check this section once again. Can we do something about it? But of course, I will undo the scenarios. Okay, just one calculation, calculate. Okay, let's wait. Okay, yeah. What about the plot? System plot, plot all cases, IPR VLP. Okay, the VLP pressure, and this one is liquid rate. I think if we can extend the picture, the plot, let's check it out. The scale, what about 10,000 to the maximum flow rate? Okay, oh, the calculation stops here. All right, you can see the actual IPR is actually like this one. The maximum flow rate is 8,300 if I'm not mistaken. Okay, should be like this, should be like this. And then maybe we can get the VLP, the intersection, if we extend the IPR and VLP. Okay, and then we will get the production rate of 1,500, like the result we get from design section. Okay, so I think again, for intermittent gas lift case, the production rate result should be obtained using this section. Okay, I think that's all. Thank you so much for watching. I hope this video is useful. I hope this video will stimulate us to learn further regarding production engineering, nodal analysis, and well modeling and simulation. And see you again in the next Prosper videos. Thank you.